we are discussing the design of a CPU. In the last class, we have read the design of arithmetic logic unit, the ALU, and today we will read the design of control unit. Control unit, as its name implies, actually it is the unit of mastering the interfaces of all other units of a CPU. So, first we see that what is the function of control unit. So, control unit translates or decodes instructions and generate appropriate signals to accomplish the desired operations. So, we have read the design of instruction set. There the instruction is fetched and then it is decoded. So, the decoding after this this decoding is done by the CPU, CU, the control unit, and then it generates appropriate signal for performing that particular operation defined by the instruction. Now, based on the contents of the instruction register, the control unit sends the selected data items to the appropriate processing hardware at the right time. To operate or to perform an operation, we need some data. So, what type of instruction it is after decoding the by CU, then the data is accessed from that particular hardware, and after operation the result is again saved to one specified hardware, and all these tasks are supervised by the CU. Now, control unit drives the associated processing hardware by generating a set of signals that are synchronized with a master clock. This is one of the important tasks of control unit, that it generates the timing signal. Normally, for all digital systems there is a master clock and all other clocks are generated from this master clock in appropriate timing, and control unit does this job. Control unit performs the following two basic operations. Actually, it works in two phases rather. One is called the instruction interpretation phase, another is instruction sequencing. So, first we see the phase 1 or the instruction interpretation phase. So, control unit reads or fetches an instruction from the memory addressed by the contents of the program counter into the instruction register. As already in the last class we have read that the current address is always the content of the program counter. So, the address specified by the contents of program counter into the instruction register, the control unit first fetches the instruction. Then the control unit inputs the contents of the instruction register. It recognizes the instruction type, first what type of instruction it is, obtains the necessary operands and routes them to appropriate functional units of the execution unit. Registers and ALU are the execution units. So, what it does? This is the important task it does, the control unit. First, it recognizes the instruction type. It is necessary because how many data are needed or to perform that particular operation, first the CU understands that thing. Then from where the data or the operands will be available. So, it gives the signal or to obtain that particular operand from particular unit. After that, now we have to perform that operation after getting the operands. Then the appropriate functional units, say the arithmetic logic unit has to perform some operation, or it has to be saved into some registers, some intermediate results or the final results. Then the CU gives a signal to registers and ALU to perform that particular operation. So, it is the first job. CU then issues the necessary signals to the execution unit to perform the desired operation. So, actually these two are related, that after getting that signals, after getting the operands, the CU issues the signal or ready signal to perform the operation. Now, functions of sequencing phase. The control unit generates the address of the next instruction to be executed and loads it into the program counter. So, all of we know that programs are normally the sequential programs. See, it is the instructions are sequentially written. So, during execution, that it takes sequentially that one instruction after another. So, when one instruction is executed or the execution is over, then the CU, the control unit, generates the address of the next instruction, and then the address, that particular address is loaded into the program counter. As always, the program counter contains the current address of the instruction or addresses of the current instruction to be executed. Now, we see that how these control units, so how these control units are designed, can be implemented. We have seen that these are the functions, mainly the instruction interpretation phase. Some functions it has to be performed, and the instruction sequencing part. Now, what type of hardware will be necessary or to implement this control unit or to perform those operations? Normally, two different methods of designing control units. One is the hardwired control, another is a microprogrammed control. Normally, the hardwired control is a synchronous sequential circuit design approach. The hardware control evolved from the fact that the final circuit is built by physically connected the components such as gates and flip flops. Now, in a microprogram control unit, all control functions are stored in a ROM inside the control unit. Now, this memory is called the control memory. So, this memory is called this is very important term, this is called the control memory, where all control functions are stored. This is called the control memory. Normally, RAMs and the PALs, the programmable array logic, already we read, are used to implement the control memory. Now, the words in this memory are called the control words, and they specify the control functions to be performed by the control unit. Now, the control words are fetched from the control memory and the bits are routed to appropriate functional units to enable various gates. The control unit is giving the all enable signals to other units, the arithmetic logic unit or the registers, and to start their operation. Now, these control words are stored in the control memory. So, the control unit is taking that control words from the control memory, and then they are routed, these bits are routed to appropriate functional memory units like registers, ALUs, etc. Now, this instruction is executed in this way. It is that called the microprogramming, and sometimes this microprogramming is called the firmware. As another approach is a hardware approach, actual physical connections are available, whereas the microprogramming we can tell as if this is a combination of software and hardware, and that is why it is called, we are calling this is a firmware. Where is the software? Because here the functional the functions or the words, control words are stored in a memory. So, these are nothing but analogous to software, and then it is routed by the control unit to the appropriate functional units to perform the operation defined by one instruction. Then these units are actually, these functional units are actually implemented by hardware. Moreover, the signals routed to the units or the data routed, these are all normally by hardware. We will see that thing, that actually the clock signals or the data bus, these are all that hardware thing. So, actually that is why the microprogramming is sometimes called the firmware. Now, we see what are the advantages or disadvantages of hardware and the microprogrammed control, as there are two approaches of control unit design. Now, microprogramming is more expensive than hardware control, because it has to access the memory, that control memory where all the functions are stored. To execute an instruction, the contents of control memory in microprogram control must be read from the memory, which is a memory access, which reduces the overall speed of CU. So, not only it is expensive, but also that it reduces the overall speed of control unit, because always accessing a memory means it will take some time. So, here the speed is reduced. The most important advantage of microprogram is its flexibility, because it is actually what is to be done, the functions that are stored in a control memory. So, only changing the software or the functions in the memory, we can change the instructions. So, the most important advantage is its flexibility. Now, many additions and changes are made by simply changing the microprogram in the control memory. So, the program that is stored in the control memory, that we can easily change, and that will change the overall design procedure or actual the processing. So, this flexibility is here. On the other hand, if it is a hardware approach, then actually it is a fixed thing. As hardware already we have defined, the hardware approach is actually physically connecting the gates, already the design is fixed. Now, if we want to change, then actually we have to redesign the entire systems, which will be very expensive as well as time consuming, and there is no flexibility at all. So, this is the one important advantage of the microprogram control design, whereas the some other disadvantages, as are already I mentioned, is expensive and moreover it is a very slow process. Now, implementation of registers, transfer of control unit. So, register transfer is the fundamental concept in the design of control unit. See how we implement it or how we declare the thing, because it is a firmware for microprogrammed. So, how we declare the register transfers. So, see we have two registers, assume we have two registers R1 and R0. So, R0 R1 R0 R1 are two registers. Now, I want to transfer the content of register R0 to R1. So, normally this is the notation is used, that R0 to R1. So, by this notation it means it denotes a register transfer, but it does not indicate the number of bits to be transferred. Say whether this register is a 8-bit register or whether it is a 32-bit register, that is never specified by this notation, or by this notation it is not understood that how many bits are transferring. So, for these purposes we have to declare the two registers in advance, that how many bits or what is the construction of that registers, how many bits are involved. So, for that we use declare registers. See here, declare registers R016, R116. This means R0, R1 are of 16-bit registers, R0, R1 are 16-bit registers. Now, by this second notation, say R014 to R11. That means, here only one particular bit is transferred. So, R11 by R11 is assigned to R014. This means the second MSB bit, most significant bit, MSB bit of R0 register is transferred to the second LSB bit, the least significant bit of register of R1 register, So, not only the whole all the bits of the register value are transferred, in this way we can one particular bit can be transferred. Now, this is actually unconditional transfer, this R014 to R11 or simply R1, simply that whole R1 bit, all the bits of R0 is transferred to R1, that also we can do. Now, this is a conditional, say E R0 to R1, here E is a enable signal. That means, enable signal controls the transfer. So, if or E may be a function of more than one variable. So, E can be generated as E is a enable signal, E is a enable signal. So, that will be on is true when one or more conditions are satisfied. So, this is a control, conditions are satisfied. Say I have two such conditions, say A, condition is A and B. If A and B, then only E is true. So, actually in that case E is actually one, say one AND gate, this type of thing. So, this is a, this enable signal is true. So, enable signal controls the transfer. E may be a function of more than one variable, and that there can be more than one input of the condition. So, now if we denote the 16-bit register transfer or the enable input controlling register transfer, say this is a register R0, this is my register R0 and this is register R1. Now, to denote that this is a 16-bit register, the bus is denoted as 16. So, this is a 16-bit register transfer from R0 to R1. Now, an enable input controlling register transfer. So, again this is a register R0, register R1, 16-bit and this is my enable signal E, and actually here the all the conditions is the output of the conditions after checked. That means, whether E is true or E is false, that will be after processing the conditions. It will give that this is a control register transfer. Now, if we that how actually what will be the hardware for each bit transfer, because earlier slide what we have seen that this is the notation, that hardware in block diagram level, the hardware notation, that all the 16 bits are, these are the 16 bits are transferred. Now, actually when physically it is being transferred, how that bitwise it is being transferred. So, each bit transfer. Now, this is a bit n of register R0. That means, this is a register R0, from there one bit is coming here. So, this is actually one bit by bit transfer. So, this is one bit. This R0 is a 16-bit register. This is a 16-bit register. Now, say the register is can be implemented by our flip flops. So, these are the output of the flip flop, that is only one bit. So, this one bit is coming to this multiplexer. So, multiplexer of 1 and 0. So, again this is my enable line. So, in this case if the enable is 1, that means if it is true, then this register bit or one bit from the register will be outputted to the mux output. This is also one bit. Then it is latched because it is a D latch. So, this is my D input, this is the Q output, and it will go to bit of register R1. And the other is the 0 input of the multiplexer. When it is enable is 0, then it will be actually the same value is again latched. So, in this can be the actual bit by bit how the bit transfer is occurred from a n bit register to another n bit register, that is this is the hardware for that. Now, the hardware implementation of the enable signal. Say here we are considering an enable signal E like that, E, say my E controlled the R0 to R1 where E is some y dot R2 1. That means, here it is a, here the enable signal is a function of more than one variable. See, this is a R2 is a register and the second LSB bit of R2, if it is 1, that means if R2 1 equal to 1 and some y value, again that y can be the output of some other circuitry that actually implementing the condition. So, if we draw the hardware diagram, say I have some condition to be checked. Say I have two values a and b, if a greater than b, then only y is 1, means true. Say this is my condition, and another is this is a, say this is the R2 registers, the second LSB bit R2 1, if it is 1, if this value is 1, then these two are ANDed, so then it will generate a E equal to 1, that means true. So, this is my enable signal generation, E is 1. So, there are y dot R2 1, then E equal to 1. So, this is a R2 is a 16 bit registers. So, this is my R2, this is a 16 bit register and this is 0 bit, 1 bit, this is 15 bit. So, this is my R2 1, this is my R2, this is my R2 1, the second LSB, and this is my y, okay. This is my y is the output of this thing, and say it is coming from some register output where it is the condition is whether R1 R0 is less than R1, what just now I have shown A less than B, or this type of condition is to be satisfied. Now, this is y, then E equal to 1, when R21 is 1 and y equal to 1, then E is 1. So, this is my enable line, this is my enable signal. Now, when enable signal is on, then only that R0 is transferred to R1. So, R0 to R1, that will, and these are all 16 bit transfer, these are 16 bit. And in this way it will occur. So, mainly the main point is that actually R1, the register has another input, and this is a actually enable signal, or that this is a control line, that whether the register transfer will occur or not, that is controlled by this E line, that enable line. Now, another very important thing is there in control unit design, and that is called the bus architecture. So, what is a bus? Buses are normally used to transfer data in and data out of a digital system. So, say we can tell that this is actually there are two units. Say I have two units inside a CPU, say unit 1, that can be my control unit, say, and say this is my ALU, the arithmetic logic unit, that is my unit 2, say ALU, or it can be any other, say this can be one input input device, and this can be my the whole CPU I can write, or the say the CU. Now, here the control unit say is accessing something from here. Okay. This can be of this type, normally this is a. So, this is a say a 16 bit line, here it is also a 16 bit. Then we are calling this is a 16 bit bus. Similarly, here also this can be a 16 bit interface line. So, this is a bus. So, buses are normally used to transfer data in and data out of a digital system. Now, two type of buses, in bus and out bus, transfers data from the external devices into processing section and vice versa. The external devices are normally the input device and the output device, and the internal devices are our different units, the arithmetic logic unit, the control unit, or the whole CPU we can think. And then the in bus and out bus are normally, the in bus is called the transfers data from the external devices into the processing section, and vice versa. So, buses are represented using register transfer notations and declaration statements. So, again how we represent the bus. So, this is bus notations. Say I have just now mentioned we have two type of bus, in bus and out bus. So, declare, again here it is just like the register transfer, declare in bus 16, out bus 16. It indicates that the digital system has two 16 bit wide data buses. Now, in bus to R0 means data on the in bus is transferred into the register R0 in the next clock. See, this is a transfer. This notation is normally this is a transfer. Here it is a equal. So, R1 15:8 is assigned to out bus, means the high order 8 bits, because 8 to 15 means the higher or the 8 MSBs. So, high order 8 bits of the 16 bit register R1 are made available on the out bus for 1 clock period. See, here it is a transfer. This notation, that by this arrow sign, we are meaning that the data available in the in bus, that is being transferred to the register R0. Here it is a assignment equal, that means the high order 8 bits that are available as the out bus for 1 clock period. So, that these are the different notations normally used for bus. Now, what will be the register transfer description when we use the bus or the registers together? We take one example. So, this is a 8 by 8 unsigned multiplication. Now, we declare registers R8, M8, Q8. That means, we have 3 8 bit registers. So, we have 3 8 bit registers. Declare buses in bus 8, out bus 8. That is, we have 2 8 bit buses, 2 8 bit buses. Now, start. See, 0 to R, in bus to M means that the operations can be performed, these two operations can be performed simultaneously. That means, it is a reset, the register R is set to 0, this is a reset register, and in bus, that means data available to in bus is transferred to the register M, and these two are parallelly performed. Now, in bus to Q means the data available to in bus, that is also transferred to the register Q. As a general rule, a comma inserted between operation can be executed concurrently. That means, this comma means this is a concurrent execution or parallel execution. That means, these two transfer are being performed parallelly. This is a concurrent execution. And a semicolon between two transfer, normally they are performed serially. So, semicolon, this and this semicolon means it is a serial execution. After this thing has been performed, then only this transfer will occur. That is, the data on in bus will be transferred to the register Q. Now, this restriction is primarily due to the data path provided in the hardware. Now, as there is only one input bus, so the operation in bus to M and in bus to Q cannot be performed simultaneously, because there are only one 8 bit in bus. So, after this data is transferred to M, then in the next clock cycle the in bus is transferred to the register Q. So, these two operations are carried out serially. However, one of these operations may be overlapped with the operation 0 to R, because this is a separate register is involved, that the register R is reset to 0 or the content of the register value should be 0. So, that we can this transfer can be performed concurrently to any one of these transfer, inverse to M or inverse to Q, because it will not affect the other one. But here as inverse is common, so we can concurrently we cannot do this transfer inverse to M or inverse to Q. These must be performed serially. And these operations are called the micro operations. All these transfers, these are called the micro operations. Because they can be completed in one clock cycle. So, these micro operations. So, first thing is 0 to R or say M to inverse, these are called the micro operations, and they are performed in 1 clock cycles. Now, in general we can tell that a computer instruction can be expressed as a sequence of micro instructions. So, this is one very important concepts, that a computer instruction, it can be expressed as a sequence of micro instructions, and micro instructions are nothing but this type of register transfer or the bus transfer. Now, another continuation of the program is that now the two registers are added. So, actually this is a clear register, and inverse to M means say the multiplicand goes to the register M, the multiplicand transferred, and then transfer the multiplier in the next clock cycle, another operand goes to Q. Now, inverse to Q. Now, R plus M to R. So, add multiplicand, this is the add multiplicand, and the result is kept to the register R, because initially it was 0. So, as if that contains the result. Now, multiplier is decremented by 1, because multiplication is nothing but that how many times we will add. So, we are actually doing Q into M, So, this is a q times m will be added. So, what we are doing initially, that one addition, after one addition q should be decremented, the multiplier, then it is decremented, and we have to continue this up to q times, because this is q into m is nothing but q times addition. M should be added q times, m plus m plus m plus up to q times, that is m q. So, mainly the normal concept of our multiplication, it has been that if q not equal to 0, then go to loop, and that means q times m should be added and the result will be kept in R, and then R to out bus, that means the result is transferred to the out bus and halt, then go to halt. So, this is the sequence of micro instructions for the program of a 8 by 8 unsigned multiplication. Now, we see that bus structure. Again, we are taking one example to explain the different type of bus structure available that is normally implemented. So, one simple addition, say the two resistor contents R1 and R2 is added and the result is transferred to R0. That means R1 plus R2 R0, R1 plus R2 is transferred to R0. Now, if we see that just to perform this addition using 3 resistors, what will be the step by step procedure. So, in the first clock cycle, so in the first time step we can tell, the contents of R1 are moved to buffer resistor B1 of the ALU. So, I have to add R1 and R2. So, what we are doing, first R1 is transferred to B1. So, B1 is my buffer resistor of ALU, because the addition must be performed by ALU. So, we have to transfer all this thing to ALU. So, first this is transferred. In the second clock cycle, so it must be separated by semicolon, because it is serial. So, B2 contains the R2. As it is a single bus, structure, that is why we need 2 clock cycle to load the operand to in the buffers of the ALU. So, that is why this is R1 to B1, R2 to B2 separated by a semicolon. So, contents of R2 are moved to buffer register B2 of ALU. And in the third clock cycle, the addition is performed. The sum generated by ALU is loaded into R0. That means, again that R1 plus R2, now already ALU has done this addition and that sum is transferred to the register R0. So, we have taken only the registers, no bus involved, only the buses are for the transferring the operands and the results. So, if we use a single bus architecture, we need at least 3 clock cycle, because we have to do the serially. Serially we have to transfer the operands and the results. So, this is the hardware for the single bus architecture. Say I have a program counter, address register, stack pointer. Okay. See, this is my ALU, this is my ALU, and here actually this is the general purpose registers. I have denoted only 3, actually it can be many more. So, R0, R1, R2 are my register pool, and these are the buffer registers. Again buffer register can be many, here only 2 we have shown. So, first that R1 should come to buffer 1 if this is my B1, then in the first clock cycle R1 will come here. So, this is a R1 to B1. Similarly, in the next clock cycle R2 will come, the value of R2. So, this is a R2 to B2, and then that 2 values will be added. So, actually this is B1 plus B2, that same thing as R1 plus R2, and then it will go to R0. So, actually this value will go to, this will be R0 to R1 plus R2. So, this is a single bus, same bus, this is a single bus. Whether it is a, this time it is a taking the operand from the register to the buffer register of ALU, and after the addition the result is transferred to the another register R0. So, by the same bus it is doing that thing. Now, if we do the same thing, that same addition by using a 2 bus architecture. Now, instead of 1 bus, say as if in the architecture there are 2 buses available. So, now we see that what will be the advantage or disadvantage. See, as there are 2 buses, so the contents of R1 and R2 are moved to the inputs of ALU concurrently, as there are 2 buses available. So, one bus will take the R1 buffer B1, R1 to B1, another bus will take R2 to B2. So, this will be in the same clock cycle concurrently. I can do this thing concurrently, and the ALU then generates the sum in the output register. In the second clock cycle, because the 2 buses are busy for transferring this content of R1 R2 to B1 B2. So, in the second clock cycle the sum from the output register is routed to R0. So, we need here 2 clock cycle. So, what will be the advantage? The advantage is that for the single bus architecture we need 3 clock cycles to do this addition, represented by these micro instructions or that execution of this micro instruction, whereas for 2 bus architecture we need only 2 clock cycles. But parallelly, as it is a 2 bus, so obviously it needs the more hardware. So, it is a hardware is more, but it is a fast thing. Now, the performance of 2 bus architecture can be improved by adding a 3 bus architecture. So, we see that if it is a 3 bus architecture, so this is the architecture of a 2 bus. The same thing, there is a register pool, again the special register group, program counter address register, and this is a memory buffer register. Again this is a pool, and actually these are the 2 buses used. These are the 2 8-bit buses. So, these are the 2 8-bit buses used. So, now it can be further improved by 3 bus architecture. So, if it is a 3 buses are available. So, what will be doing 3 buses. So, one will do that transfer R1 to R0, so R1 to B1, second will do R2 to B2, and third will do the result R1 plus R2 to R0. So, in the same clock cycle, the contents of R1 and R2 are moved to the inputs of ALU via bus A and bus B respectively. The sum generated by the ALU is then transferred to R0 via bus C. So, as now 3 buses available. So, in the only in one single clock, the whole operations will be, the addition operation will be performed. But this 3 bus architecture, obviously the system cost will increase and the complexity of the control unit design will also increase, but it will be very fast because only one clock cycle is needed. Now, another important feature. So, this is the 3 bus architecture of the 3 buses are available. Now, another important architecture or another important function of the control unit is the timing signals. See that control unit, actually one of the main tasks of control unit is properly sequence a set of operations such as a sequence of n consecutive clock signals. Now, to carry out operations, the timing signals are generated from a master clock, and that has been shown in this picture. So, this is my actual clock and some 4 timing signals, say T0, T1, T2, T3 are generated. So, this is one type of signals that one clock, this is the on period and the whole, that actually the 3 on periods of is off period. Similarly, T1 is a different one, T2 is another type and T3 is different type. So, from this master clock, it will be generated, and this is the task of control unit. This is another task of control unit. So, we have read the functions of CU and the design of CU here.